This is the chapter 21 assignment. Okay, the first one, television set connect to 120 volts outlet, consume 21 watt power. Okay, so what do we have now here is voltage is 120 volts and the power equal to 21 watt. Okay, how much current flow through the television? All right, so this is very simple because we know power equal to V times I. So voltage times current, so current equal to power over voltage. All right, B, how much time does it take for 10 million electrons to pass through the TV? All right, so here ask you about the time, right? And then we know 10 million. 10 million electrons, each electron carry E amount of charge. Okay, this is each electron carry. So total amount of charge carried by 10 million. 10 million. Okay, so total number of electrons. Each one carry this much amount of charge, right? So this is total amount of charge. And looking for time. So what do we know here is we know current, right? So charge equal to current times time. So time equal to charge over current. Okay, so we get a current from here, and we get a amount of charge here, and then divided, then you get a time, and also ask you for second. So whatever you get here, that's time. That's a second, time in second. Number two, a tungsten filament of a light bulb has resistance, so R equal to 0.07 ohm. All right, if the filament is 27 centimeter long, right? So this equals 0.27 meter. What is diameter in millimeter? All right. So looking for diameter, D, right? D equal to millimeter. All right. So what do we know here is we know resistance, right? And the resistance equal to resistivity, length over area. Okay. So looking for D. Okay. So for a circular cross-section area, right? Area equal to pi r square, and this is radius, right? So equal to pi d over 2 square. Okay, so that is diameter. Okay, so we need to find what is rho from the table, from the book, and then we can figure out, plug everything in, right? So L pi d over 2 square, right? So we know this one, we can find the rho from the book, we know length, we know pi, looking for d. Okay, let me write out the d. So d equal to 2 times square root. Okay, so basically just you look at this equation, right? So take 2 over d to the other side square, right? Equal to rho L pi r, right? Just you can change this one with this one, and then you square root, take this out, then times 2, right? So this is rho L pi r. That's it. Okay, so just plug in everything you know from the book, and also remember whatever you get here is the meter, and then you turn meter to centimeter, to millimeter. Whatever here, whatever you get here times 10 to the power 3. So you turn meter to millimeter. All right. Number 3, when a potential difference of 12 volts is applied, okay, so this is V equal to 12 volts, is applied to a wire 6.9 meter long and 0.33, okay, so D equal to 0.33 millimeter. Okay, also equal to 0.33 times 10 to the negative 3 meter. The result in an electric current of 20, so I equal to 21 amps. What is resistivity? Okay, so you see this is resistivity. Looking for rho. Okay, so what do we have here? First, looking for rho, you need to find R, right? So R equal to rho LA, and and also equal to rho if you know diameter, L pi d over 2 square. Okay, so this is resistance. And we don't know resistance. However, you can get resistance from voltage and current, right? So resistance also equal to voltage over current. Okay, so we know everything, right? So, so looking for rho, right? So, so from this equation you find resistance, and then plug a resistance here into this equation. Looking for rho, right? So rho equal to resistance times pi d over 2 square over a over L. Okay, so just this equation, right? Just this equation. Resistivity equal to resistance times cross-section area divided by length. All right. Okay. Number 4. A current of this much amps, so I equal to 0.86 amp, flow through a copper wire. Oh, they always, yeah, yes. In real life, they always give you the diameter because it's easy to measure diameter. Use caliper, right, to figure out the diameter. All right, so it's very easy to figure out, to measure. So that's usually they give you. It's hard actually to measure radius, diameter. Diameter is more easy to measure. Okay, meter. When it connect to a potential difference, so we know V equal to 15 volts. How long in meter is the wire? All right, this problem is the same as the previous one, right? So you know voltage and current, so you can figure out R, resistance, okay, and the resistance also equal to resistivity times L pi d over 2 square, right? All right, looking for L, how long in meter. Okay, so from this equation, you see this one, link them together, right? So L equal to V over I, top will be pi d over 2 square, bottom will be rho, and you see give you copper wire. Okay, so you should be able to find the resistivity from book about a copper wire. Okay, by the way, if it's in exam, definitely they will give you rho. All right, number 5. A current in a 120 volts reading lamp is 2.6 amp. If the cost of electric energy is 0.075 per kilowatt hour, how much does it cost to operate the light for an hour? All right, so what do we have here is we know power, right? Power equal to always voltage times current. Okay, and also the energy equal to power times time, right? So equal to voltage, current times time. So here we know voltage, we know current, and also we know time. Time here is 1 hour. T equal to 1 hour equal to 3600 seconds. So you get here is, you see, 120, 2.6 amp. So whatever get here is watt. Then you times 3600 seconds, right? Okay, so whatever you get here, whatever this reading is watt second. Okay. No. You don't have to turn it into seconds because looking for kilowatt hour. So let's read a kilowatt hour, right? Okay, so you don't need to change this one because we're looking for watt kilowatt hour, right? So okay, so this one you times 1 hour, right? So this one 120, 20 times 26, whatever you get a watt, then times 1 hour is a watt hour. Okay, then remember you have to turn that into kilowatt hour. So whatever you get here divided by 1,000. All right, so you turn to kilowatt hour. All right, and then this is a rate, $7.75 per kilowatt hour, and then you have this much, right? So whatever it is, this much kilowatt hour, you see, whatever number here, you calculate it. And then this will be the cost, right? So this one cancel, that is whatever cost it is. All right, next one. A 9-volt battery is connected across a terminal A and B. Okay, so what you have here is, you see, you connect 9 volts, positive 9, negative 9 volts. All right. What is the potential difference across each resistor? All right, so look at this map, right? You can tell 45 and this group connected in parallel. In parallel means the voltage is same, right? So what we have here is, so what you do here is you can simplify this whole circuit as this. Okay, so you have a resistor. So first you combine them together, right? So this will be 35, because 35 and 82 connected in series, right? So this is 1 plus 82 equal to 117 ohm, and 117 ohm, and this is 45 ohm, connect together in parallel to 9 volts. Okay, and then because they connect in parallel, so voltage is same. So basically here you have 9 volts, and here you have 9 volts. Okay, so you know the volts, you can know the, they ask you what is the potential difference of each resistor. So this guy 45 volts, you have 9 volts, right? And then you have here this one. This is a combined resistor, and then the voltage here is 9 volts. So what's the current here? Okay, so current here. Okay, current on this one, current, because this one current on this branch equal to, because the voltage here is 9 volts, right? 9 volts divided by 117 ohm, right? So it's a current. Okay, and then you come back, right? So the current, then what's the voltage on each of them, on this one and that one? Because they connect in series, so the current is the same. Okay, all right, so voltage of 35 ohm, okay, 35 ohm equal to current is 9 over 117 times 35. So this is the current times resistance, right? Voltage of the 82 ohm equal to current, because they connect in series, current is same, 9117 times 82. Okay, so same thing, this is the current, this is the resistance. All right, so you can figure out what is voltage on everybody. Okay, all right, number 7. A circuit consists of a 12 volts battery, connect to 3 resistors, 1, 2, 3 in series. Okay, so this is the circuit. Okay, so this is 12.0 volts, and then 37 ohm, 22 ohm, and 141 ohm. Find the current that flows through the battery. Okay, all right. So like this, for a circuit like this, you can always simplify into these circuits. Okay, and because they connect in series, so in series resistance equal to, you get, just add them together when you combine them, right? So this is y equal to equivalent resistance equal to 37 plus 22 plus 141 ohm. Okay, and then once you get here, you can figure out what is the current, what is the current, right? So current here, so this is a very simple circuit. Current equal to voltage from the battery, right? So epsilon divided by equivalent resistance. This is your equivalent resistance, all right? So figure out the current, okay? And then this current is the current passing through the battery and also passing through this equivalent resistance. After that, you can go back, right? And the potential difference across each resistor, all right? So you can tell what is the current here. So this current is this current the same, okay? And then you can tell this same amount of current will flow through this one, flow through this resistor, flow this resistor. Then the voltage, V1 equal to whatever current here you calculate from this equation times resistance, okay? Same idea for V2 and V3. So whatever current, everybody have same current times R2. This is R3. Okay, so you just do the work, right? Okay, more important here is you have to simplify this circuit into this circuit. That's a key point. And because they connect in series, and then equivalent resistance equal to just add them together, very simple. And then you can get the current from this simple circuit, and then you go back, right? And this current is the main current from battery. Then this, because they connect in series, the same amount of current flow through everybody. And then the voltage for everybody equal to current times each resistance. All right, number 8. A circuit consists of a battery connected to 3 resistors in parallel. Okay, so this is 1, 2, 3. All right, so 65 ohm, 25 ohm, and 170 ohm. Okay, in parallel. The total current through the resistor is 2.8 amp. Here, the total current. What does it mean? So you connect to a battery, right? And total current. This is the current from the battery. It's called total current. Okay, and this current equal to, you see, I1 plus I2 plus I3. All right. All right, the question here is, what is the EMF? First, we'll find EMF of the battery. All right, so for a circuit like this, we know current, right? So current here is 2.8 amp. All right, so circuit like this, you have to simplify it into this circuit. Okay, so one resistor and EMF. Okay, so equivalent resistance, right? Equivalent resistance of three resistors connect in parallel. Okay, so we call this R1, R2, R3. All right, so reciprocal of the total resistance equal to 1 over R1 plus 1 over R2 plus 1 over R3. Okay, so what is your equivalent resistance? Equal to 1 over, you see, this is a 65 plus 25 plus 170, 1 over 170. Okay, so you get this value, right? You get this value. And now also we give you the current. Okay, current equal to 2.8 amp, right? So from this circuit, you know epsilon equal to current times equivalent resistance. Or, same thing, right? If you know epsilon, then you can figure out what is your current. Okay, so this is equation. Then you can figure out the EMF. Second one, the current through each resistor. Okay. All right, so if you know the EMF, right, then you come back to this equation. You see, EMF, everybody together in parallel, which means voltage here, same as EMF, voltage here, same as EMF, voltage here, same as EMF. Then you can tell what is the current flow through this guy. Current 1 equal to EMF, right? Whatever you get here, divided by 65 ohm. Divided by, actually I should write R1 here equal to EMF divided by 65 ohm. Okay, so you can go ahead and figure out I2 and I3, same idea. All right, number 9. The equivalent resistance between point A and B. A and B is 33 ohm. Find the value in ohm of resistance R, right? You don't know this one. All right, let's make it simple, right? And you can tell this whole group, right? So this guy, 12 ohm, connected with this in this whole thing in series, right? And the 55 and R connected in parallel. All right. So what you can do here is you just simplify them step by step. Okay, so this is A, this is B. You see, this is 12 ohm, and what is this? This actually is it's combined 55 and R together because they connect in parallel. So in parallel will be 1 over 55, 1 over R. Okay, so same thing here, right? You see, that is how you connect in parallel. Okay, and you have to flip again. All right, then you see this guy and this guy connect in series, right? So equivalent of A and B, right, equal to 12 plus 1 over 55 plus 1 over R. And they give you equal to 33. Total equal to 33, right? Okay, well, just solve this equation. Figure out R, right? So how to solve this? Oh, very straightforward, right? So 1 over 55 plus 1 over R. Take this to other side equation, right? So 33 minus 12, 21, right? And then you flip on both ends. Flip. So 55 plus 1 over R equal to 1 over 21. Okay? Or you can just combine, put this to this side, put this one here, right? 1 over 21 equal to 1 over 55 plus 1 over R. And then put this to the other side equation. So 1 over R equal to 1 over 21 minus 1 over 55. Okay, whatever you get here, you flip it, right? Then you can figure out R equal to basically 1 over this value. Okay, that's it. Next one. Next one is, this one is a little bit a challenge. All right, so here is the circuit below include a battery with a finite internal resistance this. Okay, so you see this is the battery. Okay, this is the battery. Okay, so this one, this basically is like this. It's like a battery. Okay, positive, negative, right? And this is 12 volts. 12.0 volts. And also you have internal resistance. You have this. This guy is 0.50 ohm. Okay, so in this case, when you connect this one into a circuit, you have a voltage drop here. When you connect this whole thing into a circuit, right? So the voltage on this ends, it's not 12 volts. It will be whatever 12 volts minus a drop here, because you have internal resistance. Okay, and what's internal resistance? What is the drop? Drop based on the current. You see current flow through, right? So the reading, okay, so second question, what is the potential difference between the terminals of battery? Potential difference, okay, equal to whatever epsilon minus current times resistance. Whatever current, internal resistance, whatever current flow through, whatever current flow through. Okay, so that is the key for the solution. So you need to find the current flow through this branch. You see that? Current flow through the battery. And then the reading on battery equal to this. Okay, so if current is 0, if, okay, then the reading equal to battery equal to epsilon. Okay, so we call this open circuit voltage. open circuit voltage, open circuit voltage. But once you close the circuit, the reading will drop. Okay, so reading will be not epsilon, it will be depends on what's the current. All right. Okay, so how to solve this kind of problem? Well, we have to simplify the whole thing. Simplify step by step. All right. So first let's see here, right? So you group them step by step. First, you let me see. Ask you about 7.1 current flow 7.1 and 3.2. Okay. You see this one and this one connected in series, then in parallel with this one. Okay, and then this guy, and the whole thing in series. Okay, so let's simplify this step by step, right? So this one equal to, and also you consider internal resistance. Basically, internal resistance, this one, and this whole thing in series, right? Okay, so let's just simplify them step by step. Okay, so first one, battery epsilon 12.0 volts, right? And then 0.50 ohm, 4.5 ohm, 1.0 ohm, right? And then this is a 3.2 ohm, and then you can combine them together, right? So this one 7.1, 5.8 will be 12.9. Okay, this is the first step, right? Second step, you combine them together. Okay, same thing here, battery 12.0 volt, and then this one, okay, and then those two together, right? Okay, so together will be, you see, in parallel, right? So 1 over 3.2 plus 12.9. Okay, and then you see 1, 2, 3, 4 in series, right? So you can eventually turn to battery and one resistor, right? Okay, 12.0 volts, right? And what is this? This equal to 0.5, 4.5, 1.0, and this add all together. Just simply add them together. Okay, you get the equivalent resistance, right? And then once you get here, you can calculate what's the current. Current equal to EMF divided by equivalent resistance. Okay. All right, so that's the main current, right? Then you go back to here. So those four connect together in series, right? So the current is the same. So current from through this one, everything same, right? So you know current. And then once you know the current, then you can figure out the voltage on everybody. Especially you can figure out what's the voltage here. Okay, and once you figure out the voltage here, so voltage here is current times this resistance, this whole thing, right? Okay, and then you go here. You see that? So whatever voltage here calculated, because this one connect in parallel, which means the voltage is same. So voltage here and the voltage here is the same of this one. And then once you know the voltage here, and then we'll find the current flow through, right? 7.1. Then if you know the voltage on this 3.2, right? And then you can figure out the current on this 3.2. So voltage current on 3.2 equal to whatever voltage you hear, right? Divided by resistance. Okay. And also you can figure out the current on this branch. This branch is this guy connecting series, right? So the So the current on this branch equal to whatever voltage you calculate from here divided by, you see, combined 12.9. Oh, that's the current. So 12.9 is 7.1 and 5.8, right? So the current on this branch is the same because they connect in series, all right? So you find the 7.1, 3.2 current. How much current flows through the battery? Okay, so the battery current is here. This is the current, the main current. What is the potential difference between the terminal of a battery? Okay, so this is what we talked about it before, right? So battery potential difference equal to whatever EMF, which is 12.0 minus internal resistance times the current. You see, this is the current you get here, and the internal resistance is 0.050 ohm. Okay, so that is your reading, the voltage from the terminal of a battery. All right, number 11. Find the current in each resistor in the circuit above. This one is it's pretty. It's called a complex circuit. You have two EMF. Okay, so in this way we have to use the KVL, KCL, KVL to solve these circuits. Okay, the steps here is this: assign current on each branch. Okay, so this is I1, right? You can tell you have 3 branches, right? So you have 3 branches. So this one, you see, this is one branch. Current on this branch is I1. Current on this branch is, we call this I2. So this is a branch, right? Current on this branch, we call this I3. So this is another branch. So total 3 branches. Okay, so the first step, you just assign current for each branch. Gave a symbol, gave direction. Okay, that's all. All right, then you use KVL, KCL, and you can tell this whole thing, right? You have, this is junction, this junction actually is the same as here, right? So you only have 2 junctions, and you only have 1 KCL function. All right, so KCL function here is, you see, this tells you current through a junction, net current through a junction is 0. Let's see, let's make a in positive, out negative, right? In positive, okay, equal to 0. So this is why you see current flow in A, flow out A, flow in A, right? Then we use KVL. So this is the KCL function. Okay, this is 1. KVL, KVL, right? So this is a loop. This is another loop. Okay. So this is my loop 1, loop 2, right? Loop 1 function. Okay, let's start from here. Go through this loop this way and then go back to this one, right? So we move from, first one we meet is EMF, right? We move from low to high. Okay, voltage is 12. And then second one is we meet this 3.9, and this guy with the same direction, current direction and the loop direction the same, minus. Okay, then we meet this 9.0, this 1.2 ohm resistor. Current direction and the loop direction is the same, minus 1.2 I2, right? Then we come here, we meet this 9.8 minus 9.8, and the current direction, loop direction the same, so minus I, current is I1 equals 0. This is the function 2. And the function 3, we look at this loop 2, this loop, right? Okay, I want to start with this one, this point, then go through this loop this way, okay? All right, the first thing I meet is this 1.2 ohm. 1.2 ohm current is I2 because loop direction is up, current direction is down. So loop direction, current direction opposite, positive voltage. And then I meet this one. Current direction is this, right? Loop direction is opposite, right? So plus 6.7 I3. Now I meet this guy. I move from high to low, right? So it's a negative 9.0 volt, right? So this equal to 0. Then I go get to the same point. This equal to 0, number 3, all right? So I have 3 functions, right? I have 3 unknowns. I'm able to solve it. You combine a similar term. Okay, so make that a simple function, right? Okay, so let's simplify that. I1 minus I2 plus I3 equal to 0. This one you see 3.9 I1, 9.8 I1, so it's what? It's 13.7 I1 plus 1.2 I2. Okay, then you move 12 to other side of the equation, then you times equal to 12, right? Make sure it's right. Okay, so 12, yeah, 13.7 I1, right? Third one, right? So 1.2 I2 plus 6.7 I3 equal to 9. Okay, all right, so yeah, so you should be able to solve this. Keyword here is key method here is elimination substitution. Okay, so you see from this equation, from this, you can use I2 to represent I3. From this, you can use I2 to represent I1, right? Then you can put a substitute by I1 here, I3 here, by I2. So you can, this one, you turn this equation into only I2. And then you can figure out I2. Once you figure out I2, you can go ahead and figure out I1 and I3. All right. So A, find the current in each resistor in the circuit above, right? So you see 3.9, whatever you figure out I1, that is, right? Then 1.2, right? So this is I2. And then 6.7, 6.7 is I3, right? And then 9.8 is I1. Okay, so plug in. Determine the potential difference between the point A and B. Okay, so A and B, right? A and B will be, you see, V A B equal to VB minus VA, right? Okay, you can tell just like this, right? So this is B and A, right? So you start from here, right? Then you have a current, right? So current, whatever current times is 6.7, right? So that's a voltage, different voltage here plus voltage here, right? Then you can get this out. You can figure this out. Okay, one more thing I want to say here is this. If you solve for I1 and to I3, right? So you solved I1, I2, I3. If one of them is negative, if some of them are negative, which means you assign the wrong direction. Assume I3 is negative. Assume this is negative, right? Which means you assign this direction is your I3. Then if it turns out I3 is negative, then the real direction will be opposite. Okay, so you assign the opposite direction. So you correct that before, because initially you don't know which direction it is. Okay, so that's the solution for this one. Number 12, find the equivalent capacitance in microfarad between A and B. Okay, just step by step, right? So this one is A, and you combine the two together first, right? And then B. So this is 15 microfarad. And what's the value combine those two together? Okay, so capacitance is opposite to the way you connect the resistor together, right? So if you connect capacitance in series, then the equivalent capacitance will be, this is how you connect them together. Okay, this. Okay, because connect capacitance in series, right, equal to 1 over, okay, so this is in series. Okay, well, then you keep going, right? Then you combine this one and this one in parallel. In parallel. Okay, this one equal to, just add them together. Just add them together, 15 plus this whole group. Okay, so that will be the answer. Terminal, have to see that capacitor and the resistor, they, when you connect them together, they is opposite, the opposite way. Equation will be opposite. Okay, number 13. Terminal A and B in figure below are connected to a 18 volts battery. Find the energy stored in each capacitor. Well, so this problem and the previous one is similar, right? It's the same figure. Then you figure out the energy stored in each capacitor. Okay, so what's energy? Energy here equal to 1/2 charge voltage, also equal to 1/2 CV squared. If you know the voltage on everybody, then you can figure out the energy stored, right? Or you can figure out what's and also equal to 1/2 Q squared over C. Okay, so this is the equation. All right. Well, let's see which one is simple to you, right? So you see this one, you connect, so you get this into this circuit, right? Then you get into final circuit. Final circuit will be a battery. Oh, this one, battery. Connect to a equivalent. This is the equivalent capacitance, right? Equal to this. This is the capacitance, right? Okay, all right. And when you get here, you know what amount of charge on this equivalent capacitance. Okay, and then you go back to this circuit. You actually go back to this circuit. Once you get this one, right, you go back to this circuit. Okay, and you know the voltage on this one, voltage on this one. Okay, and once you know the voltage on this one, then you can figure out what's the amount of charge here. Okay, amount of charge equal to whatever here, right? This is the equivalent times the voltage. Voltage is 18 volts. And then you go back to here. Because they connect in series, right? The charge is the same. Charge equal to this. Okay, and then you can figure out the amount of charge on everybody, and then you can know the energy, right? You use this equation. Okay, for this one, you know, you don't have to figure out what's the charge there. You just, if you know the voltage on this one, you use this equation to figure out energy stored there. Okay. All right, next one. The equivalent capacitance of the capacitor shown below is 12.4 microfarad. Find the value of the capacitance in C. Let me see, in C. Okay, so this one. All right, so how to connect them together? Just a step by step, right? A, B, A, right? So this one, this one, this one, this one. First, you combine them together. This connect in series, right? So in series will be this, right? So this one compared together in series, right? This one equal to 1 over 12.0 plus 8.35. Okay, and then this connect in parallel. right? So next step, A, 1, B, and they together in parallel, right? Parallel, just add them together. Okay, add them together was be 4.25 plus this thing, right? So this thing will be, okay, and then this guy and this guy connect in series, right? Let me see. Oh yes, yes. So this one, you connect this one. Yeah, you connect, combine to this one, right? So this is in series, right? So this is C in series. What's this? Well, first you calculate this out. Calculate this out, right? So this is C. So this will be. So now next one is A, and you have something here, A, B, and then you have this, right? You have this. In series is 1 over C plus 1 over this whole thing. Okay, and then connect together in parallel. Just add them together, right? So at the end, right? So capacitance between A and B is 12.4. This also equal to 7.22 plus this whole group. Okay, solve for C. Number 15. The switch on a RC circuit is closed at t equals 0. RC, okay, switch, right? All right, so we know this is 6.0 volts, R equal to 92 ohm, C equal to 28 microfarad. All right, 28 Farad. How much charge? Okay, you're looking for micron charge, right? Then you don't have to turn to Farad, just a microfarad. Okay, is on the capacitor at time equal to 4, so you know time equal to 4.0 millisecond. All right, so we have to use this equation. So Q, right, in terms of time equal to C epsilon 1 minus E negative T over RC. Use this equation. Okay, looking for time, right? So now looking for time equal to this, right? So at t equal to 4.0 times 10 to the negative 3 seconds, amount of charge equal to, you see, just put time here, just substitute time, this term by this value. Okay, C, you know C, right? You know epsilon 6, 1 minus E. Okay, so this equal to, just like plugging everything in. So 28, 6.0, 1 minus E negative T 4.0 times 10 to the negative 3. Okay, R divided by RC, right? So R will be 92. C, you have to put SI units. Okay, to make the bottom in the unit of seconds. Okay, so RC here, you have to use 92 times 28 times 10 to the negative 6. You have to submit this value. Because in this case, you have seconds. Top will be milliseconds, right? You turn to top will be negative 3, bottom will be negative 6, something. Okay, so you have to make that. Top is seconds, bottom is seconds, so you can make this E function dimensionless. Okay, so just plug in. And then you figure out what's the amount of charge. So looking for how much charge in microcoulomb is on the capacitor. Why it's microcoulomb? Because you use this is a 20. You use 28, right? So this is a micron farad. Okay. let's whatever get is with micron coulomb. Key point here is in this equation, okay, this part, top is negative T RC. You have to make the, if it, because bottom, top is in units of a second, bottom you have to make that in units of a second so that you can cancel. So this is e to the power of this, right? Top unit second, bottom unit second. You have to make them same unit so that they cancel. Then this whole thing became dimensionless. All right. Number 16, a flash unit for a camera has a capacitance. This is capacitance. What resistance in kilo ohm, right, is needed in the RC circuit if the flash is to charge to 90% of its full charge in 21 seconds. Okay, so what do we know here is time equal to 21 seconds, right? So Q, use this equation, right? So time equal to C epsilon 1 minus e to the negative time over RC. Okay, so you 90% of the full charge. Okay, so what's the full charge? This is the full charge. 90%, right? So this is 90% C epsilon. So C epsilon is the full charge. And the Q now is 90% of full, right? So this is equal to, so this is 90% of the full charge. Okay, so C cancelled. And, T, 21 seconds, right? So plug 21 seconds here. And RC, if you use R, kilo ohm, right? And C will be, doesn't matter, right? So you turn that into Faraday, you turn that into ohm, then whatever you solve this equation, solve this. Solve for, so only unknown here is R, because you know T, right? You know C, looking for R. Then you solve this R in ohm, then you turn to kilo ohm, okay? To solve for this. All right, so that's all for this assignment.